Hi, we will see Chebyshev's inequality now. Chebyshev's inequality provides an upper bound to the probability that the absolute deviation of a random variable from its mean will exceed a given threshold. Please note, not within, will exceed a given threshold is very important. And upper bound means it is always less than or equal to that prediction value. And absolute deviation of a random variable from its mean means absolute value of x minus mu. Mu is the mean, x is the variable. And the given threshold means we can give it in two ways, a comma b, which are equidistant. I will tell you what is equidistant. Equidistant from the mean, or mu plus or minus k sigma, that is k times the standard deviation sigma. So here is a sample and here is a population. So x bar is the mean of the sample, mu is the mean of the populations. In both the cases we can apply this inequality. So we can use x bar as mu in the problems. Probability of absolute value of x minus mu greater than or equal to k times standard deviation is always less than or equal to 1 by k squared. So what do you mean by the other part of the probability? Probability of the absolute value of x minus mu less than k times standard deviation is greater than 1 minus 1 by k squared, because total is 1. Probability of this plus probability of this is the total probability, which is 1. So this is a sample, this is a population. No assumption is made about the distributions. It can be any distribution, need not be normal. It is a skewed distribution to the left. Only variance is noted here. If the variance is small, it is unlikely to be too far from the mean. It will be close to the mean. It is the least we can tell about the dispersion of a distribution. It is applicable to both parametrics and statistics. Consider a random variable x with a finite mean mu and variance sigma squared. Probability of absolute value of x minus mu less than k times standard deviation is greater than 1 minus 1 by k squared. This is what we will be using in the problems. We will derive it from Markov's inequality. If x is a non-negative random variable and a is greater than 0, then the probability that x is at least a is at most the expectation of x divided by a. If x is greater than or equal to 0, the same thing I am telling it in a mathematical mode. If x is greater than or equal to 0 and a is greater than 0, then probability of x greater than or equal to a is less than or equal to expected value of x divided by a. What we will do is, we will take the deviation. Probability of x minus mu, absolute value of x minus mu, is greater than or equal to c. That is x minus mu I have taken, instead of a I have taken c. Same as probability of square of this value, because this is already a positive value, therefore this is also a positive. Greater than or equal to c squared is less than or equal to expected value of x here, x minus mu whole squared here, and which is nothing but variance. Expected value of the square of the deviation is variance. So sigma squared by c squared. So probability of x minus mu, absolute value of x minus mu greater than or equal to c is less than or equal to sigma squared by c squared. A random variable has a mean mu 8 and variance sigma squared 9. Find probability of absolute value of x minus mu greater than or equal to 6 and probability of minus 4 less than x less than 20. There are two problems. We will see the two probabilities. Mu is equal to 8 and sigma is equal to square root of variance, that is square root of 9, 3. And k sigma is equal to 6 here in the first problem. This is k times the standard deviation is 6. Therefore k is equal to 6 divided by standard deviation, which is 3. So 6 by 3 is 2. So k is equal to 2. Therefore probability of modulus of x minus mu greater than or equal to 6 is equal to probability of modulus of x minus mu greater than or equal to k, that is k times standard deviation, k is 2, is equal to less than or equal to 1 by k squared, that is 1 by 4, that is 0.25. And what is the probability of the opposite? Probability of absolute value of x minus mu. When I say modulus of x minus mu, that means absolute value of x minus mu less than 6 is equal to greater than or equal to 1 minus 0.25, that is greater than or equal to 0.75. So the answer for the first question is greater than or equal to 0.75. For the second problem, we will subtract mean from all the values. Minus 4 minus mu less than x minus mu less than 20 minus mu. Mu is equal to 8, therefore probability of minus 4 minus 8 is minus 12, less than x minus mu, less than 20 minus 8 is 12. And k sigma is 12, therefore k is equal to 12 by sigma, sigma is 3, therefore k is equal to 4. Now the probability is obtained as 1 minus 1 by 4 squared, that is greater than or equal to 15 by 16. So probability of modulus of x minus mu less than 12 is greater than or equal to 1 minus 1 by 4 squared, that is greater than or equal to 15 by 16. We'll see another problem. Number of products produced in a factory during a week has a mean mu is equal to 50 and variance sigma squared is equal to 25. What do you say about the probability of production that will be between 40 and 60? So mu is equal to 50, sigma is equal to 5. Probability of 40 less than x less than 60 is equal to, as usual, we will subtract the mean 50 from all the values. 40 minus 50 is minus 10, x minus mu, less than 60 minus 50 is 10. So k sigma is 10. So k sigma is equal to 10, k is equal to 10 by 5 because sigma is 5. So that is 2. So probability of modulus of x minus mu less than 10 is greater than or equal to 1 minus 1 by 2 squared, that is greater than or equal to 0.75. We will see another problem. Various states minimum wages has a mean mu of 6.51 lakhs and standard deviation of 2.39 lakhs. At least what percentage of states minimum wages were anywhere between 3.51 to 10.51 lakhs. So here mean is 6.51, sigma is 2.39 given, lower limit is 3.51 lakhs, A is 3.51 and B is upper limit 9.51 lakhs. So k is equal to B minus mu by sigma. That is 9.51 minus 6.51 is equal to 3. 3 by sigma is equal to 1.255. So probability of 3.51 less than x less than 9.51 can be converted by subtracting mean from all the sides. So probability of 3.51 minus mu less than x minus mu less than 9.51 minus mu, that is probability of minus 3 less than x minus mu less than 3, that is 1.255 times standard deviation. So probability of modulus of x minus mu less than 3 is greater than or equal to 1 minus 1 by k squared. K we have found out, that is 1 minus 1 by 1.255 squared, that is greater than or equal to 0.376. So at least 37.6% of times states minimum wages will be anywhere between 3.51 to 9.51 lakhs. We will see the last problem. Here the problem is different. We will have to find out the interval given the probability. Chief Executive Officers of California has a mean salary of 5.4 million with standard deviation 1.8 million. What is the interval in which at least 80% of California CEOs' salaries lie? We have to find out the salary interval for 80% probability. So mu is equal to 5.4, sigma is equal to 1.8, probability is 0.8. We'll have to find out A and B, lower and upper salary limits. So probability of modulus of x minus mu less than k sigma is equal to 1 minus 1 by k squared, that is given as 0.8. Therefore, we can find out k is equal to 2.236. Right? The k sigma is equal to 2.236 into 1.8 because sigma is 1.8, k is 2.236 and that is 4.025. And B is equal to mu plus k sigma, A is equal to mu minus k sigma, A is equal to 1.375, B is equal to 9.425. Therefore, at least 80% of California's CEO's salaries lie between 1.375 and 9.425 millions because between A and B. Thank you very much.